May 14, 1942, Quincy, Massachusetts. Inside the cavernous assembly hall of the Fall River shipyard, a vessel sat half-complete on building way number 7 that looked absolutely wrong to every maritime engineer who saw it. At 328 feet long, with a beam of 50 feet, she had the dimensions of a respectable coastal freighter, but her bow doors gaped open like a mechanical mouth, her flat bottom sat barely 5 feet deep, and her entire forward section could swing open to disgorge vehicles directly onto a beach. The LST, landing ship tank, represented a vessel type that traditional naval architects considered an abomination against centuries of ship design principles. Deep draft hulls provided stability, pointed bows cut through waves efficiently. Watertight integrity meant sealed compartments, not massive doors that opened the entire bow to flooding. Yet here stood hull number 461, and she embodied every violation of conventional wisdom because Andrew Jackson Higgins and a handful of desperate naval planners had concluded that winning the war required ships that could do the impossible. The mathematics were brutal and non-negotiable. Allied forces needed to invade occupied Europe. That meant landing armies with their tanks, artillery, trucks, and supplies directly onto hostile beaches thousands of miles from friendly ports. Traditional cargo vessels required deep-water harbours and extensive dock facilities. The Germans had destroyed every major port along the French coast, or fortified them into impregnable strongpoints. Landing craft could carry infantry and light equipment, but Sherman tanks weighing 30 tons each, long-tom artillery pieces, supply trucks loaded with ammunition, none of these could fit in small landing craft that infantry used. The solution demanded a ship that could cross oceans like a freighter, survive combat like a warship, and drive directly onto beaches like an amphibious vehicle, then discharge 200 tons of vehicles and cargo through bow doors in under 2 hours. Every experienced naval architect declared this combination impossible. Ships that could beach themselves lacked ocean-going capability. Ocean-going vessels required deep drafts incompatible with beach landings. Large bow doors compromised structural integrity fatally. John Niedermair, chief naval architect at Bethlehem Steel's Quincy Yard, stood beside the incomplete LST with Commander William Baxter of the Bureau of Ships. Both men were studying the specifications with expressions mixing skepticism and desperate hope. Niedermair had spent 32 years designing warships, cargo vessels, and passenger liners. Nothing in his experience suggested this design could function. His private notes, preserved in the Bethlehem Steel archives, revealed the engineering establishment's assessment in May 1942. The LST violates fundamental principles of naval architecture. The flat bottom provides inadequate stability in rough seas. The bow doors create a massive structural weakness at the point of greatest stress. The shallow draft of 3 feet 9 inches forward means any significant wave will break over the deck. The ballast system required to maintain trim when the bow is empty after unloading represents engineering complexity I have never encountered. If this design works, it will rewrite textbooks. If it fails, it will kill everyone aboard. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The crisis that created the LST had been building since Dunkirk in May 1940. When the British Expeditionary Force evacuated France, they abandoned virtually all their heavy equipment on the beaches. Tanks, artillery, trucks, all lost. The lesson was clear. Armies without heavy equipment cannot fight mechanized warfare. But the reverse lesson proved equally vital. Armies cannot recapture occupied territory without the ability to land heavy equipment directly onto hostile shores. Winston Churchill understood immediately. Within weeks of Dunkirk, he sent an urgent request to President Roosevelt. Britain needed ships capable of landing tanks directly onto beaches. Not at ports, ports would be destroyed or defended. Not using cranes, transferring equipment from ships to smaller craft. Too slow. Too vulnerable, direct beach-to-shore capability for vehicles weighing up to 30 tons. The British had attempted preliminary designs throughout 1940 and early 1941. The results were consistently disappointing. The HMS Boxer, an experimental tank landing ship built in late 1940, could carry only 3 tanks, required perfect beach conditions, and took over 6 hours to unload. The design was abandoned. British yards were already overwhelmed building destroyers, corvettes, and merchant vessels to replace ships sunk by U-boats. They lacked capacity to experiment with revolutionary amphibious designs. America's entry into the war in December 1941 transformed the equation. The combined chiefs of staff, meeting in Washington in January 1942, confronted a strategic reality that demanded solutions. The Allies would invade North Africa, then Sicily, then Italy, then France. Each invasion required landing mechanized armies on defended beaches. The landing craft in current inventory could handle infantry and jeeps. Nothing existed that could land the Sherman tanks, tank destroyers, and heavy artillery that mechanized warfare required. Admiral Ernest King, Chief of Naval Operations, assigned the problem to the Bureau of Ships with a deadline that made experienced engineers wince. Operational LSTs needed to be in production by June 1942, just 5 months away. The preliminary British designs would serve as starting points, but American yards needed to design, test, and prepare for mass production of a vessel type that had never successfully operated. The man who would transform the LST from theoretical concept to mass-produced reality was not a naval architect with decades of maritime experience. John C. Niedermair held impressive credentials, certainly, but the revolutionary insights came from an unlikely source. A 47-year-old mechanical engineer named Otto Klemperer, who had spent his career designing automotive assembly equipment for General Motors and had never built anything that floated. Klemperer arrived at the Bureau of Ships in February 1942 as part of the wartime mobilization of industrial engineers. His assignment seemed straightforward: analyze the British LST designs and determine how to manufacture them efficiently in American shipyards. What he discovered instead was that the British designs, while innovative in concept, were catastrophically difficult to build at scale. The British Mark I LST required approximately 8 months to construct using traditional shipbuilding methods. Hull construction followed conventional practice: keel laid, frames erected, plates riveted or welded in sequence from keel to deck. The bow door mechanism, requiring massive hinges and hydraulic systems, could only be installed after the hull was substantially complete. The ballast and trim system needed extensive piping networks threaded through compartments after structural work finished. Klemperer examined the construction sequence and saw immediate parallels to the manufacturing bottlenecks he'd solved in automotive plants. His analysis memo, dated March 5, 1942, laid out observations that would transform LST production. Current construction approaches treat the LST as a ship built using sequential methods appropriate for conventional vessels. This is incorrect. The LST should be understood as a mobile warehouse with propulsion. Its function is to transport material and discharge it rapidly. The vessel should therefore be designed for parallel assembly using prefabricated modules, exactly as we construct truck bodies and railroad cars. The Bureau of Ships' response was initially dismissive. Ships were not trucks. Maritime engineering involved stresses, stability calculations, and watertight integrity that automotive engineers couldn't comprehend. Klemperer persisted by focusing not on naval architecture theory but on production arithmetic. At 8 months per LST, American yards might build 15 per month across all facilities by late 1942. The combined chiefs had calculated that the invasion of North Africa alone would require at least 200 LSTs, with hundreds more needed for subsequent operations. At 15 per month, reaching that inventory would take 13 months. The invasion schedule allowed 8 months from production start to North Africa landings. The numbers simply didn't work. Either the LST design had to be radically simplified for faster construction, or the invasion plans needed to be postponed, giving Germany more time to fortify Europe. Admiral King reviewed Klemperer's analysis in late March and made a decision that horrified traditional naval constructors. He authorized Klemperer to redesign the LST specifically for rapid parallel assembly, with naval architects providing technical support rather than leading the design. The revolution began with Klemperer's observation that the LST hull was fundamentally a rectangular box with a pointed front end. Unlike conventional ships with curved hulls, complex stern shapes, and hydrodynamic optimization, the LST's mission required cargo volume and beach landing geometry. Her flat bottom was dictated by shallow draft requirements. Her slab sides provided maximum internal volume. She didn't need to be beautiful or efficient. She needed to be buildable in massive numbers quickly. Klemperer proposed breaking the LST into 7 major modules that could be constructed simultaneously in different locations, then transported to a final assembly yard and connected in a matter of days rather than months. The engineering team at Bath Iron Works in Maine, assigned to develop detailed plans, initially resisted the concept before Klemperer's manufacturing logic proved overwhelming. The bow section, containing the massive bow doors and the complex ramp mechanism, represented the most technically challenging component. Traditional construction required building this section in place as part of the hull assembly. Klemperer proposed constructing complete bow sections as standalone units in a dedicated facility. A specialized shop could build nothing but bow sections, developing expertise and tooling for that single task. Workers would become extraordinarily efficient at a limited set of operations, rather than being skilled generalists who could build any part of any ship. The engineering specifications called for bow doors measuring 14 feet high and 34 feet wide, creating an opening through which tanks and trucks could drive. The doors needed to be watertight during ocean transit but capable of opening quickly during beach operations. The structural loads were enormous. When closed, the doors had to withstand wave impacts in Atlantic storms. When open, they formed the foundation for a discharge ramp supporting 30-ton vehicles. Bath Iron Works engineers calculated that a conventionally constructed bow section with properly reinforced doors would require 12 weeks of work. Klemperer proposed a modular design where the entire bow assembly, including doors, hinges, hydraulic systems, and structural framing, would be fabricated as a complete unit in a jig that held all components in precise alignment. Once perfected, each bow module would take just 72 hours to assemble from pre-cut and pre-formed components. The midship cargo hold sections followed similar logic. Rather than building these spaces as integral parts of a hull constructed from keel up, Klemperer specified 3 identical rectangular modules, each 40 feet long, 50 feet wide, and 24 feet deep. These cargo modules were essentially steel boxes with no complex curves, no difficult geometry, just straight plates welded at 90-degree angles. A production facility could stamp out cargo modules like railroad boxcars, using the same components repeatedly. The first module might take 2 weeks. The 50th module, built by workers who'd repeated identical operations 49 times before, might take 4 days. The 100th module, 3 days. The engineering team established dimensions that allowed cargo modules to be constructed on railway flat cars, then transported by rail directly to assembly yards. The engine room module represented the most complex prefabricated section. Unlike the British design, where engines were installed after the hull was substantially complete, Klemperer proposed building complete engine rooms as drop-in units. General Motors diesel engines, reduction gears, propeller shafts, auxiliary generators, fuel tanks, all would be mounted on structural frames in engine assembly facilities, tested as complete units, then transported to final assembly yards as functioning power plants. The stern section, containing steering gear and crew quarters, became another standardized module. The superstructure, with bridge and officer accommodations, was fabricated as a separate unit. Even the tank deck, the massive flat surface where vehicles would be secured during transit, was specified as prefabricated steel sections that bolted together during final assembly. Critics pointed out obvious problems. Prefabricated sections had to fit together with extraordinary precision. A cargo module built in Pittsburgh needed to mate perfectly with a bow section built in Cleveland and an engine room built in Detroit. Tolerances of fractions of an inch across structures 50 feet wide seemed impossible to maintain when components came from different facilities. Klemperer's solution borrowed directly from automotive mass production. precision jigs and fixtures that guaranteed repeatability. Every facility building LST components received master jigs, steel frameworks that held components in exact positions during assembly. Workers didn't measure and fit pieces individually. They positioned components in jigs, and the jigs ensured correct alignment. The first piece built in a jig might require adjustments, but once the jig was perfected, every subsequent piece would be identical within thousandths of an inch. The breakthrough that made 72-hour final assembly possible came from reconceptualizing what building a ship meant. Traditional construction started with nothing and gradually created a complete vessel through thousands of individual operations performed in strict sequence. Klemperer's approach started with 7 nearly complete major assemblies, then connected them in a process more akin to assembling a child's building blocks than traditional shipbuilding. At the final assembly yard, the process would unfold with mechanical precision. Day 1, the keel sections, prefabricated steel beams, would be positioned and connected. Massive cargo hold modules would be lowered by crane onto the keel structure and welded in place. Day 2, the bow section, complete with doors and ramp system, would be positioned and connected to the forward cargo hold. The stern section, with steering gear installed and tested, would be connected to the aft cargo hold. The engine room module, with engines already broken in and tested, would be dropped into its designated space and connected to propeller shafts. Day 3. The superstructure would be positioned. The tank deck sections would be bolted down. Electrical and plumbing systems, pre-assembled as much as possible, would be connected between modules. The vessel would be flooded with ballast, test, trim, and stability. By hour 72, a complete LST would exist where an empty building way had stood 3 days before, not a shell requiring weeks of fitting out, but an operational vessel ready for sea trials within days. The entire concept seemed fantastical to experienced shipbuilders, until Klemperer pointed out that Liberty ships were already being built in 42 days using similar prefabrication approaches. The LST, simpler in many ways than a Liberty ship, should logically build even faster once the modular system was perfected. The Bureau of Ships approved the modular design in April 1942, with explicit understanding that this was a desperate gamble. If the modules didn't fit together properly, or if the prefabrication approach produced structurally weak vessels, the entire program would collapse, taking Allied invasion plans with it. Construction of the first modular LST, designated LST 461, began in May 1942 across 11 different facilities scattered through Pennsylvania, Ohio, and Massachusetts. The bow section for LST 461 was fabricated at the American Bridge Company facility in Ambridge, Pennsylvania, 20 miles north of Pittsburgh. The facility had never built ships. For 60 years, American Bridge had constructed steel structures. Bridges, buildings, industrial frameworks. The company's engineers understood massive steel fabrication, precision welding, and load-bearing calculations. They'd built the Bayonne Bridge spanning 1,300 feet across the Kill Van Kull and the steel framework for multiple skyscrapers in Manhattan. When the Bureau of Ships contract arrived in April 1942, American Bridge's president initially questioned whether the Navy had sent the specifications to the wrong company. His chief engineer, Thomas Radcliffe, reviewed the bow section drawings and recognized immediately that this was a bridge component disguised as a ship part. The structural calculations, the load paths, the reinforcement patterns, all followed principles American Bridge knew intimately. Radcliffe's team built the master jig for bow sections in 8 days, a massive steel framework that held every component in precise 3-dimensional position. The jig itself weighed 40 tons and required a dedicated assembly bay with overhead cranes. Once completed, it became a template that guaranteed every bow section would be functionally identical. The first bow section, started on May 4th, required 17 days to complete, as workers learned procedures and identified interference problems where components didn't fit properly. Adjustments to the jig eliminated these issues. The second bow section took 11 days. The third took 8 days. By the 6th bow section, started on June 2nd. The American bridge crew completed assembly in 71 hours and 40 minutes. The cargo hold modules came from the Dravo Corporation shipyard in Pittsburgh, a facility that built river barges and towboats. Dravo's experience with flat-bottomed vessels made them ideal for LST cargo sections. The rectangular geometry of cargo holds presented no unusual challenges. These were essentially oversized barges with watertight bulkheads. Dravo established a production line where 3 cargo modules were always in various stages of completion. Structural frames were assembled first, massive steel I-beams forming the skeleton. Deck plates, bottom plates, and side plates were then welded to the frame structure. The welding sequence followed principles recently developed for Liberty ships, center outward patterns that minimized residual stress and prevented warping. Each completed cargo module was hydrostatically tested, flooded with water to verify watertight integrity before shipping. By early June, Dravo was completing 1 cargo module every 4 days, with 3 modules in simultaneous production, providing a steady output. The modules left Pittsburgh by rail, loaded onto specialized flat cars with the cargo holds secured by massive timber cribbing. The engine room modules presented the greatest technical challenge and the most impressive manufacturing innovation. General Motors, which had been mass-producing diesel engines for locomotives and industrial applications since the 1930s, established a dedicated LST engine room assembly facility at their electromotive division plant in LaGrange, Illinois. The approach borrowed directly from locomotive production. Rather than installing engines into hulls, GM built complete power plants on structural frames that could be lifted as single units. Each engine room module contained 2 diesel engines, each producing 900 horsepower, reduction gears, generators, fuel tanks, cooling systems, electrical panels, and even the control stations from which engineers would operate the machinery. The innovation that made this possible was the structural frame system designed by GM's chief mechanical engineer, Harold Wallace. The frame consisted of welded steel beams forming a rigid box structure, every component mounted to this frame, with engines bolted to precisely machined mounting pads, piping and electrical runs following predetermined paths, and all connections standardized. Most remarkably, each engine room module was tested as a complete unit before leaving LaGrange. The engines were started, run at various loads for several hours, and every system was verified functional. When an engine room module arrived at final assembly, it wasn't a collection of parts requiring installation and testing. It was a proven operational power plant, ready to be connected to propeller shafts and ship's electrical systems. The first engine room module required 6 weeks to complete as GM engineers developed procedures and solved integration problems. By late May, the production time had fallen to 18 days. The target was 12 days per module, which GM's production planners believed achievable once workers fully mastered the assembly sequence. The Fall River Shipyard in Quincy, Massachusetts, was designated as the final assembly location for LST 461. Fall River was one of America's premier shipyards, with a history dating to 1883 and a reputation for quality warship construction. The yard had built battleships, cruisers, and destroyers using traditional methods where every vessel was unique and construction took years. John Niedermair, Fall River's chief naval architect, watched the first LST components arrive in mid-June with a mixture of curiosity and professional skepticism. The bow section arrived by rail on June 15th, secured to a specialized flat car designed to carry the 35-ton assembly. Cargo hold modules arrived on June 17th and 18th. The engine room module, the heaviest component at 60 tons, arrived on June 20th. Niedermair's inspection revealed something that simultaneously impressed and disturbed him. The components were extraordinarily well made by industrial fabrication standards. Welds were clean and consistent. Dimensions matched drawings within acceptable tolerances. But these pieces had been built in facilities that manufactured bridges and locomotives, not ships. The workers who'd welded these sections had never built anything that would face Atlantic storms. His report to the Bureau of Ships, dated June 22nd, captured the traditional maritime community's unease. The LST components now at Fore River represent manufacturing quality adequate for structural applications. Whether they represent maritime quality adequate for ocean service remains to be demonstrated. I note that the bow section shows no evidence of riveting, depending entirely on welded construction. The cargo hold modules use steel plate thickness that appears marginally adequate for the hydrostatic pressures they will experience. The engine room module, while ingeniously designed for rapid installation, contains no redundancy. A single failure could disable the vessel completely. We will proceed with assembly as directed, but I cannot recommend these vessels for unrestricted ocean service without extensive sea trials proving their seaworthiness. The 72-hour assembly timeline that Klemperer had projected was about to face its first real-world test. The schedule called for assembly to begin at 6 a.m. on June 24, 1942. If the modular concept worked, LST 461 would be structurally complete by 6 p.m. on June 27. Day 1 began with positioning the keel structure, prefabricated steel beams that formed the vessel's backbone. Traditional keels were laid plate by plate, but the LST keel came in 3 sections that were lowered into place by overhead cranes and connected with bolted splice plates. By noon, the entire keel assembly was secured to the building blocks, the temporary wooden structures that would support the vessel during construction. At 2 p.m., the first cargo hold module was lifted by a massive gantry crane capable of handling 150 tons. The module, weighing 48 tons, was positioned over the keel structure. Skilled riggers guided it into place using tag lines, while surveyors used precision instruments to ensure alignment within 1/8 of an inch. By 4:30 p.m., the module rested on its mounting points, and welding crews began connecting it to the keel structure. The second and third cargo hold modules were positioned on day 1, working into the evening under floodlights. By midnight, all 3 cargo modules were in place, and temporary tack welds held them securely. The day's progress astounded the Fore River workforce. Traditional hull construction would have required weeks to reach this point. In 18 hours, the vessel's basic structure existed. Day 2 focused on connecting the bow and stern sections and installing the engine room module. The bow section, with its 14-foot-tall doors and complex ramp mechanism, was the most challenging component to position. The doors had to align precisely with the tank deck. The bottom of the bow had to match the forward cargo hold's bottom plates within millimeters to ensure smooth vehicle passage. At 8 a.m., the gantry crane lifted the bow section. For 40 minutes, riggers and surveyors worked to achieve perfect alignment. When the bow finally settled into position at 8:45 a.m., the supervising naval architect verified that all critical dimensions were within specification. Welding crews immediately began permanent attachment, working simultaneously at 20 different locations around the bow-to-hull junction. The stern section installation proceeded more quickly. Its geometry was simpler, and alignment was less critical. By 2 p.m., the stern was positioned and welding was underway. At 4 p.m., the engine room module arrived at the building way, suspended from the gantry crane. This moment represented the ultimate test of the modular concept. The engine room had to drop into a space formed by the 3 cargo hold modules, connecting to mounting points, propeller shafts, and ship's systems. If dimensions were wrong by even a few inches, the module wouldn't fit, and the entire assembly would halt while workers cut and modified structures. The engine room descended slowly into its designated space. Workers on scaffolds guided it with taglines while surveyors monitored clearances. At 4:38 p.m., the module settled onto its mounting points. The propeller shaft alignment, critical for preventing vibration and bearing failures, was checked immediately. The shafts aligned within specifications that would have been considered excellent in traditionally built vessels. By midnight of day 2, the engine room was secured, and crews were connecting piping, electrical cables, and control systems between the engine room and the rest of the ship. The vessel now had a recognizable shape: a hull, bow doors, a stern, and engines. What remained was installation of the superstructure, the tank deck, and completion of thousands of system connections. Day 3 brought the superstructure, a 3-deck structure containing the bridge, officers' quarters, and crew accommodations. This unit, fabricated at Four Rivers' own shops, was lifted into position at 8 a.m. and secured by noon. The tank deck, consisting of pre-fabricated steel plate sections with tie-down fittings for securing vehicles, was laid and welded throughout the afternoon. By 6 p.m., on June 27th, 72 hours after keel positioning began, LST 461 was structurally complete. Every major component was installed and connected. The vessel looked like a ship with proper hull form, superstructure, and equipment. What remained was testing and the inevitable adjustments required for any prototype. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The sea trials of LST 461 began on July 10, 1942, 2 weeks after structural completion. The intervening time had been spent on system testing, adjustment of the ballast system, and crew training. Commander John Merrill, assigned as the vessel's first commanding officer, approached the trials with carefully controlled skepticism. Merrill had served on destroyers and cruisers throughout his 20-year naval career. Ships, in his experience, were graceful vessels that cut through waves with pointed bows and moved with the sea rather than against it. The LST, with her flat bottom, blunt bow, and doors that opened the entire forward section to the ocean, violated every principle of seaworthy design he'd learned. His private journal, donated to the Naval Historical Foundation in 1978, recorded his initial impressions. LST 461 looks like a floating warehouse designed by someone who'd never seen the ocean. Her appearance suggests she will wallow like a bathtub in any seaway, and the bow doors inspire no confidence whatsoever. The British Mark I LST we examined last month at least looked like a ship, albeit an ugly one. This modular American version looks like steel boxes welded together by enthusiastic amateurs. I fully expect she will prove unseaworthy, and the entire program will return to conventional construction methods. The first test involved simply getting the vessel into open water. LSTs drew only 3 feet 9 inches forward when empty, shallow enough to navigate channels and approaches that would ground conventional ships. But that shallow draft meant minimal keel area for directional stability. The vessel was predicted to be difficult to steer, requiring constant helm corrections. As LST 461 proceeded down the channel from Quincy toward Massachusetts Bay, Merrill discovered the steering predictions were accurate but manageable. The ship required attention from the helmsman, who had to anticipate turns well in advance and apply rudder generously. But she responded predictably, and after an hour of practice, the helmsman developed feel for her handling characteristics. The open ocean test began in moderate conditions, seas running 4 to 6 feet with winds at 15 knots. Traditional destroyers and cruisers handled such conditions effortlessly. LST 461 handled them awkwardly but successfully. The flat bottom meant waves struck the hull with solid impacts, rather than sliding smoothly along curved plates. The vessel's motion was harsh, uncomfortable, but not dangerous. She rolled moderately, pitched noticeably, but maintained course and speed. The critical test came when Merrill ordered the bow doors opened while underway in coastal waters. This maneuver represented every traditional naval architect's nightmare, opening massive doors in the bow, compromising the vessel's watertight integrity, while waves struck the hull. If the door mechanism failed, if the ramp broke loose, if water flooded the tank deck, the vessel could be lost within minutes. At Merrill's order, crew members activated the hydraulic system that opened the bow doors. The 14-foot tall doors, each weighing several tons, swung outward slowly. The ramp, a massive steel structure designed to bridge the gap between bow and beach, lowered into the deployed position. Water did indeed wash over the ramp in moderate swells, exactly as predicted, but the tank deck, positioned 2 feet above the waterline, remained dry. The bow structure, despite having a massive opening where solid steel should be, maintained structural integrity. The vessel's speed dropped from 11 knots to 8 knots due to increased drag from the open bow, but she remained controllable and seaworthy. Merrill ordered the doors closed. The hydraulic system retracted the ramp and swung the doors shut in just under 4 minutes. Watertight dogs secured the doors. Inspection revealed no leakage, no structural damage, no problems. The doors worked exactly as designed. The full load trials conducted on July 16th revealed the LST's true capability and the ultimate validation of the 200-ton payload specification. The vessel was loaded with a test cargo designed to simulate combat conditions. 4 Sherman tanks, each weighing 30 tons, 6 2.5-ton trucks loaded with ammunition, 3 jeeps, and miscellaneous cargo, bringing the total load to 196 tons. With this cargo secured to the tank deck, LST 461 sat deeper in the water, drawing approximately 8 feet aft. The additional weight should have made the vessel sluggish and difficult to handle. Instead, the behavior improved. The deeper draft provided better directional stability. The additional weight dampened the harsh motion in waves. Speed under load was 9 knots, adequate for convoy operations. The beach landing test, conducted on a Massachusetts beach selected for its gradual slope, represented the final validation. At Merrill's direction, the helmsman drove LST 461 directly toward the beach at 6 knots. The flat bottom allowed the vessel to proceed into water depths that would ground any conventional ship. At 400 yards from shore, the depth was only 6 feet. At 200 yards, only 4 feet. The vessel grounded gently when the bow touched sand in 3 feet of water. The bow doors opened, the ramp lowered, and its seaward end rested in 18 inches of water. A test Sherman tank, operated by an Army crew briefed on the procedure, started its engine and drove down the ramp onto the beach. The entire discharge took 12 minutes for the test tank. Had all 4 tanks been aboard with drivers ready, Merrill estimated the full unloading time at 35 to 40 minutes. This compared favourably to the British specification of 2 hours and dramatically exceeded the capability of any existing landing craft. Extraction from the beach required the most remarkable feature of the LST design, the ballast system that Niedermair had identified as unprecedented engineering complexity. With cargo discharged, the vessel sat grounded with her bow firmly on the beach. To extract, the crew pumped seawater into ballast tanks in the stern, causing the aft section to settle deeper into the water. Simultaneously, water was pumped from bow ballast tanks, lightening the forward section. The shift in trim changed the vessel's angle, lifting the bow. After 15 minutes of ballasting operations, the bow lifted free of the sand. The engines reversed, and LST 461 backed away from the beach into deeper water. The procedure worked flawlessly on the first attempt, a remarkable achievement given the complexity of the ballast calculations and the potential for disaster if the vessel had become hopelessly stuck. Commander Merrill's final report on sea trials, submitted to the Bureau of Ships on July 22, represented a complete reversal of his initial skepticism. LST 461 has proven herself seaworthy, capable, and surprisingly reliable for a prototype vessel employing revolutionary construction methods. Her handling characteristics, while unconventional, are manageable with trained crew. Her cargo capacity meets specifications. Her beach landing and extraction capabilities exceed expectations. The modular construction approach has produced a vessel as functional as traditionally built ships in a fraction of the construction time. I recommend immediate approval for mass production. The Bureau of Ships didn't wait for Merrill's recommendation. Orders for LST production were already being placed based on the successful completion of structural assembly. The modular construction system that had seemed so risky in April had proven itself by July. Now the challenge shifted from proving the concept to scaling production to unprecedented levels. The arithmetic was simple but daunting. The combined chiefs of staff had calculated requirements: 200 LSTs for Operation Torch, the invasion of North Africa scheduled for November 1942, another 300 LSTs for the invasion of Sicily, planned for summer 1943, additional hundreds for subsequent operations, culminating in the cross-channel invasion of France. The total requirement exceeded 1,000 LSTs, needed within 24 months. Traditional construction methods, even using prefabrication techniques similar to Liberty ships, would require 40 to 50 days per LST. At that pace, American yards might build 600 LSTs by mid-1944, leaving a shortfall of 400 vessels that would force cancellation or postponement of amphibious operations. Otto Klemperer's modular system, if scaled to multiple production lines, offered a solution. The 72-hour final assembly time for LST 461 was achieved using components built one at a time in scattered facilities. If those facilities expanded to build multiple modules simultaneously, and if additional component suppliers were recruited, production rates could increase dramatically. The Bureau of Ships established a production plan that would have seemed fantastical before the LST prototype proved feasible. 10 final assembly yards would be established, each capable of assembling one LST per week once fully operational. Supporting these assembly yards, 23 component manufacturers would produce bow sections, cargo hold modules, engine room assemblies, and other major components. The Pittsburgh area became the center of LST production due to the concentration of heavy steel fabrication facilities. American Bridge Company expanded their bow section production from 1 bay to 5 bays, each with its own master jig. Dravo Corporation established 3 separate facilities building cargo hold modules. General Motors added LST engine room production to facilities in Chicago and Cleveland in addition to the original LaGrange plant. By September 1942, the production system was operating at scale. Component manufacturers were completing modules every few days. Final assembly yards were receiving steady streams of components and launching completed LSTs weekly. The 72-hour assembly time proved sustainable. Some vessels took longer due to component delays or quality issues, but others were completed faster as workers mastered procedures. The first production LST completed after the prototype, LST 301, was assembled at Dravo's Naval Island Yard near Pittsburgh in August 1942. The facility, located on an island in the Ohio River, seemed an unlikely location for a shipyard building ocean-going vessels. The island sat nearly 1,000 miles from the Atlantic Ocean, connected to the sea only by rivers and canals. Yet this inland location proved advantageous. Steel arrived by rail or barge from Pittsburgh mills just miles away. Components manufactured throughout the region converged on Naval Island. Workers lived in nearby communities rather than overcrowded coastal cities. The Ohio River provided adequate water depth for launching and initial testing. LST 301, assembled in 6 days from keel to launch, proceeded down the Ohio River to the Mississippi, down the Mississippi to New Orleans, then across the Gulf of Mexico and Atlantic Ocean to Norfolk, Virginia. The 1,800-mile river journey served as an extended shakedown cruise that revealed problems before the vessel entered combat service. By December 1942, American yards had completed 48 LSTs. The production rate was accelerating weekly as more yards reached full operation and component suppliers refined their processes. The first combat employment came during Operation Torch in November 1942, though most LSTs arrived too late for the initial landings and were used for follow-up logistics operations. The Sicily invasion in July 1943 represented the first large-scale use of LSTs in their intended role. 229 LSTs participated, landing the equivalent of an armored division directly onto hostile beaches. The performance validated every design decision. LSTs drove directly onto beaches in the pre-dawn darkness, discharged their vehicles and cargo in under 2 hours, and extracted themselves before German artillery could organize effective counter-battery fire. The Normandy invasion on June 6, 1944, employed over 230 LSTs. These vessels, built in Pittsburgh and other inland cities by workers who'd never seen the ocean, crossed the Atlantic, survived the worst English Channel weather in decades, and landed American and British forces directly onto German-occupied France. The modular construction system that had seemed so risky in 1942 had produced vessels that proved tougher and more reliable than traditionally built ships. Lieutenant Robert Beeman, commanding LST 388 during the Normandy landings, recorded his experience in a letter written 3 days after D-Day. "We hit Omaha Beach at H+90 minutes, approximately 8:30 a.m. German artillery was active, and shells were landing in the surf zone. I drove this vessel directly onto the beach through a narrow gap between obstacles. We grounded firmly, opened the bow doors, and began discharging our cargo of 6 Sherman tanks, 4 tank destroyers, and 8 trucks. A German 88mm shell struck our port quarter, penetrating the hull but fortunately hitting no critical systems. We continued unloading. The entire discharge took 1 hour and 14 minutes from grounding to last vehicle ashore. We then executed ballasting procedure and extracted from the beach under intermittent artillery fire. The vessel sustained 3 additional shell hits during extraction but remained fully operational. We returned to England for minor repairs, reloaded, and made a second landing run 36 hours later. This ship, built in 72 hours from prefabricated sections by workers in Pittsburgh, has proven tougher than many traditionally built vessels I've served on during my 16-year naval career. The welded construction that critics claimed would be weak has survived combat damage that would have sunk riveted ships. The modular design allows rapid damage repair. The bow door mechanism has operated flawlessly through 7 landing cycles. I am impressed by this ungainly, uncomfortable, indispensable vessel. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.